All right, so I'm going to talk about the other half of what Ian Cohen talked about, sort of the initial goal of the ACES sounding rocket mission. These were the two pictures that Craig Heisselman took at the time of launch. If you look hard enough on YouTube, you can find a video of this. I wouldn't recommend it because there's some commentary by a certain person. So I just want to give a little bit more credit besides the co-eyes that I had on the previous page, but these are the remainder of the ACES team that provided instruments and also some expertise. So I just want to go into discussing the context of how a discrete auroral arc and what it has to do with MI coupling and in the context. And 50 years ago, I've heard 40 thrown around, but 50 years ago, Bostrom came up with this paper, which in my opinion is probably one of the most seminal papers in MI coupling, in which he proposed these two different current configurations to explain auroral electrojets. And where you have closure within the ionosphere, closing this magnetospheric ionospheric circuit. In addition, more with respect to auroral arcs, he also devised this sheet, the auroral arc as being sort of like a strip, which is something I'm going to talk more about. And also the idea of the polarization electric field was developed in this paper as well. So it's really a fundamental paper discussing a lot of the various aspects, which to my understanding are still sort of the name of the game for talking about auroral electrodynamics. And more of the current picture, this is a picture taken from Markland, which I like. From what I understand, the FAST satellite and a lot of other satellites have talked about a parallel electric field accelerating electrons from the plasma sheet to KeV energies, which carry this upward field-aligned current. They cause these discrete auroral arcs within the ionosphere. Markland and a bunch of guys, like in the mid-90s, came up with this idea of black aurora carrying the return current or the downward field-aligned current. And so you have to have some kind of closure between these two regions in order to close this current loop. And so I would argue that a discrete aurora is really an ideal system to study this upward-downward field-aligned current system in a more localized region than in the global sense. So with that in mind, there was quite a while ago, the guys at Iowa proposed the Auroral Currents and Electrodynamic Structure Sounding Rocket mission. And one of the key features of this mission, to my knowledge, this is one of the few multi-point observations of a discrete auroral arc system. So the idea was to fly these two payloads, this high-altitude payload, which I'm going to now call ACES High for the remainder of the talk, to fly at about 350, 360 kilometers in the F region, and then a low-altitude payload called ACES Low, which was to fly mainly in the E region, and with ACES High to measure electrodynamics and plasma parameters, sort of the magnetospheric inputs into the lower part of the ionosphere, and then ACES Low to make similar measurements and similar observations of currents, fields, and particles at this lower altitude region, and to try to deduce something about the current structure. A couple of points is that these were designed to be launched nearly simultaneously. In reality, there was actually a 90-second delay between the ACES Low launched 90 seconds after ACES High. We also included the Pfizer radar as well, and all sky imagers where Pfizer, there were a lot of beams placed down the nominal trajectory, so you could get good coverage between both payloads. And also it gives a greater context in terms of what we actually launched into. So if you're interested in more information about the ACES mission and what it observed, I'd recommend you read Kaeppler et al., which is in the AGU monograph on auroral physics. So what this talk is going to focus on is a case study. Kaeppler et al. Identified 3 auroral arc crossings. And the first crossing is what's really going to be talked about, where both payloads cross through this quasi-stable arc, which you can see here. And it's termed quasi-stable because generally it's east-west, but there is some motion and brightening associated with it. So H indicates ACES High, L is ACES Low, and these are the magnetic foot points. I also have on here the cardinal directions, and these are with respect to the field. So this is north and east, with respect to like the electric and magnetic fields corresponding to the local geomagnetic systems. You can see that there is a little curvature in this arc. But ACES High enters into this arc, and there was a little bit of brightening that happened in the all-sky right before ACES High enters. It traversed the arc in about 30 seconds, and then ACES Low, so this is showing the exit. You can see that the arc is brightened a little bit more. About 40 seconds later, ACE's low then enters through this generally brightened arc. I should also mention you can even see it here that it's moved a little bit equatorward in the time frame that ACE's high is actually traversed through. ACE's low then traverses through this much more stable, brighter arc. And as ACE's low was exiting the arc, it was actually rapidly fainting in the all-sky video. And if you're interested in seeing an all-sky video, just come and talk to me. I couldn't quite get it working on the Mac here. I apologize for that. But this shows the sheet, sort of the closest thing we had to a sheet in this event that we're going to use for this model that I'm about to discuss. So to actually interpret the observations that we made, we have been developing a model that follows in the footsteps of a Mallinckrodt 1985 model. From what I understand, I think this was one of his last papers he published before he unfortunately exited the field. There's a variety of model assumptions that go into this, and quite a few significant assumptions, particularly being steady state, electrostatic. It's long, so there's no variation along the arc or along the sheet. And then there's also the assumption that the electric fields map down from the magnetosphere into the ionosphere. And so the idea is that we're developing this model, but we're going to use observations from the in situ observations and radar observations when relevant to actually drive this model. So I'm using the ACE's low electron precipitation flux, and we're going to use that and fit a precipitation model to that, which is actually the Evans model, which I'll talk about in the next slide. From that model, we're going to calculate the Hall and Pedersen conductivities, and then from that, combined with the electric fields, which map down from ACE's high, we can then calculate the three-dimensional currents of JX, JY, and JZ in sort of this nominal sheet arc configuration. Using the ACE's high magnetic fields, we can then calculate Ampere's law along the track velocity or the track direction of the payload to get the parallel field-aligned current, which we can then compare back and forth between this method using gradients in the conductivities and electric fields versus what we get from the magnetometer, and hopefully that they'll agree, which I'll show you some of those results. One side note is you might wonder, why didn't you use ACE's high here? The reason why is, and this is sort of a subtle point, but it turned out that we had a failure in our detector, so the energy is only swept up to 500 eV instead of the full range our detectors were designed to do from 100 up to 16 keV. So we're actually using the ACE's low electron flux for this modeling portion. And assuming that the flux that we observed there would have been what we would have observed had ACE's high had the full energy range. So to discuss the model that we use, this is the Evans model. So 40 years ago, Evans came up with this model, which was also another seminal paper in auroral physics, which discusses that if you have a plasma sheet electron distribution, which is accelerated by an infinitely thin parallel electric field, you accelerate these electrons downward. As they continue to move down along the magnetic field line, there's an exchange of parallel to perpendicular velocity to conserve the magnetic mirror force. When these collide with the ionosphere and start to scatter or ionize the ionosphere, you get these secondary electrons which were emitted off. And Evans characterized these originally from a Banks 1974 paper. And if these secondaries don't have enough energy to overcome this infinitely thin parallel potential drop, they'll reprecipitate back onto the ionosphere, creating additional ionization and scattering. This effect continues to happen with the idea, kind of like being a bouncing ball, that you throw on the ground if you're playing basketball or something, that with each subsequent bounce of secondary electrons, less and less are created. So it attains a steady state after a few iterations. Okay, so applying this model, what we did is this is an example, the black corresponds to an example of the differential energy flux that was observed on ACE's high. And what we did is we fit this beam. We actually used a kappa distribution, and so you can see the parameters, and you can see that it fits very well to a power spectrum. And so we fit this kappa distribution, and then we ran the backscatter portion of the model where this discontinuity corresponds to the location of the potential drop. And you can see that our fit is very, very good with a kappa index of 3 along with the other magnetospheric parameters. And also we do a very good job fitting the secondary electrons. From that, we then calculate the total parallel number flux. So this is the number flux into the ionosphere. The height ionization, equilibrium height ionization using expressions from Semeter and Kalamabadi. The background electron density, and then from that, the Hall and Pedersen conductivities as a function of altitude. Oh, that is really too bad. I did not expect that. Okay, well, this really is disappointing. I'm sorry about that. So I was going to show you this really nice electron spectrogram, but apparently it's not going to show up. So, but that being said, I guess I can discuss the conductances. So from this, we actually had very good agreement between the electron flux and the and our model. You can take my word for it or come see me later. So one thing I was going to point out was that one thing we saw was that the kappa index actually changed midway through the flight, or midway through traversing through this arc, which is interesting because it became more Maxwellian later on in the flight. And that's something that I don't entirely understand, but I think it's an interesting observation. We also calculated out the field-aligned integrated Pedersen conductivities and Hall conductivities. And one thing you'll note is that I also calculated out the Robinson expressions. And the Pedersen conductance does a very good job matching with the Robinson expressions. The Hall conductance does a reasonably good job, in terms of shape, but there's this difference in magnitude. And then we also integrated out the field-aligned current. So moving forward from this, now that we had the conductivities and a so-called good fit, along the payload trajectory, JX, since we assume that there's no variance in the other direction, we minimized one component, which was the EY component, and I used polynomial fits. So for the EX component and the EY component, that's what the red line indicates. And I did that so I could take smooth numerical derivatives more than anything. And so we minimized the EY component. We found that there is a direction of minimization. We multiplied it, and then we took the numerical derivative of the X component along the payload track. And so from that, we derive field-aligned currents, where you generally have an upward field-aligned current corresponding to this auroral arc, which is consistent with what you would expect along with downward field-aligned currents on either side. Similarly, we also did this using Ampere's law along the payload track in the same frame as the electric field. So we have, again, fit, and then we calculated the field-aligned current, and we see that we're generally, again, getting upward field-aligned current over this region of the arc. The issue is that the magnitudes are off by about a factor of 10. And that's really kind of where it's at right now, and it's been something I've been thinking about and trying to understand. So it seems like with these two methods, you should get something that would come out to be the same, and I wonder how much of it could be diverting off into this Y direction, which we're just assuming is there is no divergence in that direction. So I'm just going to skip that. I'm just going to go straight to my conclusions in the interest of time. So if you want to believe me on this, we did fit to a kappa distribution. It's actually a very good fit, and I'd be more than happy to show anybody in here. We did calculate the field-aligned currents using 3 different methods where there's generally good agreement between the field-aligned current from the directly integrating the model fluxes versus the magnetometer. We found about a factor of 5 to 10 difference between the field-aligned currents from gradients in the electric field and conductivities along the arc, which I wonder if that could be current diverting off along the arc, and that's something that I'd like to investigate further. There's other issues as well, whether our steady state conditions were violated, what the impact of arc curvature, and I also showed, I just made this on Friday, and but we did actually observe increased Joule heating over the arc, which from what I understand from some previous literature is actually different than what was observed by Evans 1977. That's a really good example, where he actually observed less Joule heating over the arc and more particle precipitation. So with that, thank you.
since Strangeway is in the room, when we look at fast data, it seems usually that the upward current region is where the arcs are, and there is really no downward current right next to them. That's another region. So, I mean, looking at that, I wouldn't expect an upward and downward current being next to an arc. Do you agree with that, Paul, mostly? I mean, this could have been an exception. I'm not saying that, but it's just
usually fairly broad, very smooth.
smooth, yeah, and you don't have a reverse current right there.
Again, I don't know how long the track your crosscut is.
It was about 25 to 30 kilometers. Yeah.
Tom?
At the beginning of your talk, you listed assumptions, and one of them was that the electric field maps from high to low altitude, and another one was that there was an E-parallel accelerating the electrons. Now, a compulsive purist might argue that those two assumptions are contradictory. On the other hand, it's quite possible that they're very nearly consistent. I'm wondering if you have checked on that.
So the whole argument about parallel electric fields mapping from the magnetosphere to the ionosphere and through the ionosphere that's something I've been trying to wrap my head around for a long time, because frankly I don't know. But I think I understand the spirit of your question, and I think what I would say is that since we're looking at 300 kilometers, we're just interested in the 300 kilometers down, which I think that's pretty reasonable. I'm not trying to map out from 10 RE or something like that. So,
is it possible that could contribute to this disagreement between the different methods of estimating the field line currents?
I haven't thought about that.
Okay, thank you.